Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about projections of the planes. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now today we will be discussing about projections of the oblique plane which happens to be inclined with respect to the horizontal plane as well as the vertical plane. Here we have been provided with a circular lamina having 60 millimeter diameter, and this circular lamina is resting onto the horizontal plane on a point 1 of its circumference, and this lamina happens to be inclined to the horizontal plane. And usually whenever a lamina happens to be inclined to the horizontal plane, we are provided with the angle of inclination of the surface of the lamina with respect to the horizontal plane. But in this particular case, the lamina happens to be inclined to the horizontal plane in such a way that its plan, it is represented as an ellipse with minor diagonal of 30 millimeter. That is, the minor diagonal or the minor axis will be 30 millimeter, while in the plan the major diagonal will be represented as 60 millimeter. Since in this case we are not provided with the angle of inclination, so using the information that the reduction of the diagonal which is passing through the point 1, this diagonal will see foreshortening from 60 millimeter to 30 millimeter, as this diagonal 1, 7 will be inclined with respect to horizontal plane at a certain angle. So once we draw this particular ellipse in which the minor axis will be 30 millimeter while the major axis or the major diagonal will be 60 millimeter, so we can evaluate the angle of inclination of this circular lamina with respect to the horizontal plane. And in the second instance, the plan of this diameter which we have obtained, that is this minor axis diameter of 30 millimeter. So the plan of the diameter through this point 1, this apparent length of the diagonal or minor axis 1, 7. So this will be further inclined at an angle of 30 degree with respect to the vertical plane. So here we are required to draw the orthographic projections of this lamina and evaluate the angle of the inclination of the surface of the lamina with respect to the horizontal plane. Now here in this case, since the circular lamina happens to be inclined with respect to the horizontal plane in the first instance, so to begin with we are going to assume that this lamina, it is contained by the horizontal plane. Why? Because one of the points of the circumference of this lamina will be resting onto the ground. So this lamina will be contained by the horizontal plane, and thereafter we are going to incline the surface of the lamina with respect to horizontal plane at a given angle over there. So here we are going to obtain the true shape of this circular lamina onto the horizontal plane, that is in the top view. And this top view true shape projections will be drawn below the XY reference line. And while we are going to look at the circular lamina from the front side, we are going to obtain the edge view projections of this lamina located onto the XY reference line, because this lamina is contained by the horizontal plane. So here this is the orientation. So in case of circular lamina, we are going to get no issues regarding the orientation. So only thing is it will be resting on the ground on one of its point number 1 over here. So let us proceed with the evaluation of the orthographic projections of the circular lamina. So we know that the circular lamina diameter happens to be 60 millimeter. So we are going to draw a circle, and now we are going to divide it into 12 equal parts. So each of the segment of the circle will be measuring 30 millimeter. So we have marked these points as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So total 12 segments we have been able to obtain, and this is the measurement of the diameter, that is equal to 60 millimeter. So this is the top view true shape projections of the circular lamina which have been obtained onto the horizontal plane over here. And because we have obtained the true shape projections onto the horizontal plane, so these projections will be drawn below the XY reference line. And while this lamina is contained by the horizontal plane, so as we look at this lamina from the front view over here, so we are going to obtain the projections of all of these points, that is all the 12 points of this particular circular lamina. They will be projected onto the XY reference line, and the edge view of this lamina will be obtained onto the horizontal plane. Having obtained the front view, edge view projections over here, now we know that this lamina, it is resting onto the ground on point 1, right? The orientation of the inclination of the surface of the lamina with respect to the horizontal plane should be like this. But the problem over here is this, that we have not been provided with the angle of inclination of this lamina with respect to the horizontal plane. Rather, we are required to evaluate or measure this angle of inclination. So then how do we measure this angle of inclination of the surface or the plane of the lamina with respect to HP? Now, here we have been provided with the information that the lamina is inclined with respect to the horizontal plane in such a way that the plan of this lamina, it is an ellipse. That is, we are going to obtain an ellipse over here in such a way that this diagonal, because you see, even when the angle is given, we are going to incline this edge view at a certain angle. We are going to obtain the foreshortening of this diagonal 1 dash 7 dash over here in the top view projection. So whatever is the angle, accordingly there will be certain amount of foreshortening of this diagonal 1 7. But now, rather than providing us with the information regarding this angle, we have been provided information about the length of this particular foreshortening. That is, the foreshortening of this particular diagonal 1 7, it has happened in such a way that from the original 60 millimeter, this diameter in the plan view has been reduced to 30 millimeter over there. So with this reference, now you can see, we know the distance between the end projectors of the diagonal 1 7 in the plan. This is the end projector corresponding to the point 1. This is end projector corresponding to the point 7, because here we are going to get the diagonal 1 7 located over here. So here we will be getting the diagonal 1 7 in the plan over here. So this reduction will be corresponding to certain amount of inclination, certain extent of inclination of this edge view with respect to the horizontal plane. And we know that lesser the angle of inclination, lesser will be the reduction or foreshortening of this diameter in the apparent length. More the angle of inclination, more will be the reduction in the apparent length of this diagonal over here in the top view projection. So now this reduction has been specified, that is 50% reduction, that is 30 millimeter will be the amount of or the length of this diagonal 1 7 which will be obtained in the plan projection view over here, whereas this diagonal 4 10 will still be parallel to the horizontal plane. So here, corresponding to this diagonal 4 10, we are going to obtain true length of this diagonal projected over here. That is why we say that this will be transformed as an ellipse in the top view projection. So one of the diagonal, that is the major axis or major diagonal, will be 60 millimeter, whereas the other diagonal which is inclined with respect to HP will be reduced from 60 millimeter to 30 millimeter. So the end projector of point 1 is given, end projector of the point 7 is given, and the distance between the end projectors of points 1 and 7 which correspond to this diagonal over here, which is going to be inclined with respect to horizontal plane. So the distance between the end projectors has been provided to us as 30 millimeter. So once we know the distance between the end projectors, now we can evaluate the angle of inclination of this edge view with respect to the horizontal plane. Now we can see that we know this length, distance between point 1 dash and 7 dash is available with us. So we will be measuring this distance 1 dash 7 dash, and we will be marking this distance between these two end projectors. So from this point we'll keep the needle point of the compass over here. Open compass is equal to the edge length which we are able to see in the elevation view, that is 1 dash 7 dash. We will be marking this distance over here onto the second end projector corresponding to the point 7. So points 1 dash and 7 1 dash, they have been located. Then according to the distances which are available corresponding to the other points onto this edge view, now same distances will be plotted alongside this front view projections which are obtained onto the vertical plane corresponding to this inclined lamina. So the moment we draw this edge length between these two projector lines, so we are able to evaluate the angle of inclination of the surface of this circular lamina with respect to the horizontal plane. So the angle theta, that is the second part of the problem, has already been evaluated. So we have been able to evaluate the angle of inclination of the plane of the circular lamina with respect to horizontal plane. Now having evaluated this angle theta, now the top view corresponding projections of the 12 points of the circular lamina, now we are going to evaluate. So how they will be evaluated? From these 12 points in the elevation, we are going to draw the vertical projector lines, and from these 12 points in the plan projection view, we are going to draw the horizontal projector lines over here. So wherever we are going to obtain the intersection of the corresponding projectors, we will be able to obtain 12 points of this plan projection view over here. Now you can see this is vertical projector through the point 4 1 dash. Wherever it intersects with the horizontal projector obtained through the point 4, the point 4 1 has been located into the top view projection. Similarly, next horizontal line will be passing through the points 3 and 5. So please see, we have drawn a horizontal projector line passing through 3 and 5. So let us locate the points 3 1 dash and 5 1 dash in the front view. So this is the point 3 1 dash. We can see from 3 1 dash we draw a perpendicular downwards, and wherever it intersects with the horizontal projector through point 3, this point is the point 3 1. Similarly, we have drawn vertical projector from the point 5 1 dash. So from point 5 1 dash we have drawn a vertical projector downwards. Wherever it intersects with the horizontal projector line drawn through point 5, we obtain the point 5 1 in the top view projection. Similarly, here you have got 2 and 6. So same horizontal line will be passing through 2 and 6. So onto this horizontal line, wherever projectors corresponding to 2 1 dash will be intersecting, point 2 1 will be located. Wherever projectors from the point 6 1 dash, they are going to intersect, point 6 1 has been located over here. Similarly, there is going to be one horizontal line corresponding to the points 1 and 7. So this horizontal line, wherever it intersects with the vertical projector from 1 1 dash and 7 1 dash, these are the extreme points over here. 1 1 dash is this extreme, 7 1 dash is this extreme. So below the 1 1 dash, the point of intersection with this horizontal line will provide 1 1. Below the 7 1 dash, we draw the vertical projector line, and its intersection with this horizontal line originating from point 7 provides us with the location of the point 7 1. Similarly, you have got one horizontal projector line corresponding to the points 12 and 8. So let us find out points 12 1 dash and 8 1 dash in the elevation. So we draw a perpendicular down from 12 1 dash, wherever it intersects with this horizontal projector line drawn through the point 12, we obtain point 12 1, and from 8 1 dash we have dropped a perpendicular in the downward direction. Wherever it intersects with the horizontal line drawn through the point 8, we are able to obtain 0.81. Again, you have got 2 points giving you the same horizontal projector line. These points, they happen to be 9 and 11. So corresponding to 9 and 11, we have obtained one horizontal projector line. So let us obtain projectors corresponding to 11.1 dash and 9.1 dash. So the vertical projector through 11.1 dash, it is going to intersect with this line which is drawn through the point 11 at this particular point. Similarly, here from the point 9.1 dash, we have dropped a vertical projector downwards, and wherever this vertical projector from 9.1 dash, it intersects with horizontal projector through the point 9, we obtain the point 9.1 over here, and finally we have the point 10 over here. So from point 10 we have drawn a horizontal projector, and wherever it intersects with the vertical projector drawn through the point 10.1 dash, so this intersection will provide us with the location of 10.1. So having located these 12 points in the top view projections, the moment we join them, we can see a perfect ellipse. It has been obtained in the top view projection. Now, what is the characteristic of this perfect ellipse plan projection, or the apparent shape of the circular lamina which we have been able to obtain in the top view? So the characteristics are that this diagonal 4, 1, 10, 1. So this is still true length. Why this is true length? Because even after inclination of this lamina with respect to horizontal plane at an angle theta, it is still parallel to the horizontal plane. So this diagonal still, it happens to be true length. But because of the inclination of this diagonal 1, 1 dash, 7, 1 dash with respect to horizontal plane at an angle theta, now we have been able to obtain foreshortening of this diagonal from 60 millimeter to 30 millimeter. Now this is the apparent length which has been provided to us as a minor axis of the ellipse, that is equal to 30 millimeter. Now in the second phase, we have been provided with the information that the plan of the diameter, so this is the plan of the diameter 1171. So please check, this we will call as 1171 as the plan of the diameter 17. So this is making an angle of 30 degree with the vertical plane. So now we have to reorient and redraw or rotate this ellipse in such a way that at an angle of 30 degree, so we have marked an orientation line inclined at an angle of 30 degree with respect to the vertical plane. So this ellipse need to be reconstructed over here in such a way that this diagonal 1, 7, so 1, 7 diagonal, that is the plan of the diagonal, should be located at an orientation of 30 degree with respect to this particular orientation line. Now, how do we transfer this ellipse over here? Again, using the rectilinear distances principle. So how that can be done? You can see. So now 2 corner points we have marked over here. 2 corner points, right? This point and this point. This point is representing point 1. This point is representing point 7. So 1 and 7 points we have already drawn over here. Now we can mark, you can check, there are 5 intermediate projector lines. 1, 2, 3, 4 and 5, right? So line 1, projector line 1, projector line 2, projector line 3, projector line 4 and projector line 5. Now this point will be lying at the center. We can see this point. It is lying at the center. So corresponding to this point, you can see points 4 and 10 will be located, and they will be located at this distance from the center and this distance from the center. So we are going to mark this length and this length. The moment we mark this length, point 4 and 10 will be located at these two extremes over here. Similarly, the moment we mark this distance, please check the distance of point 3, distance of point 5, distance of point 11, distance of point 9, they are all equal. So if I measure this distance, that is distance of center line to point 11, same will be the distance of center line to 3, center line to 5, center line to 9. So this way I will be marking from the center this distance and this distance. So please check, from center line we have marked this distance and this distance, and then whatever distance we had marked, so 4 distances we are going to mark: 1, 2, 3 and 4. So the 4 points, which are these 4 points? 3, 5, 9 and 11. So these 4 points, they have been located. Now we are left with another 4 point. Now please check, from this center mark this distance, from this center mark this distance. So please check, from this center we have marked this distance, from this center we have marked this distance, and now 4 points are located. Which are those 4 points? 2, 6, 8 and 12. So once I measure this distance, the distance of center line to point 2, it is same as distance of center line to point 12, distance of center line to point 8 and distance of center line to point 6. So once I measure only one distance, so these 4 distances I will be able to mark. So from this point measure same distance over here, from this point measure same distance. So another 4 points. Which are these 4 points? 2, 6, 12 and 8. So this way all the 12 points we can locate over here. So you can see these 12 points we have been able to reproduce using this rectilinear distance method. So using the rectilinear distance method, we have been able to rotate the ellipse which we had obtained in the plan projection previous view into the new oblique view. So this is oblique view in a way because these projections, they have been drawn when the circular lamina happened to be inclined with respect to horizontal plane at an angle theta, and the circular lamina is further inclined with respect to vertical plane at an angle of 30 degree. So this way the plan projections corresponding to the oblique lamina which happens to be inclined to HP and VP, they have been obtained. Now once we have obtained the top view projections corresponding to this oblique lamina, now the corresponding projections of the oblique lamina in the front view, they need to be obtained. So again the procedure will remain the same, that is, from all of the 12 points in the front view, the horizontal projectors we have drawn over here, from all the 12 points in the plan projection view which we have obtained corresponding to the oblique lamina, now vertical projectors we are going to draw over here. Now wherever the intersection of the vertical projector through each one of these points will be occurring with the horizontal projector drawn through the corresponding point, we are going to obtain the location of the points in the front view projection. So let us see how we can obtain the 12 points in the front view. So from point 1, 2 over here, that is point number 1, vertical projector, please check, we have drawn over here the vertical projector drawn through the point 1. Please check, wherever it intersects with the horizontal projector drawn through the point 1, 1 dash, point 1, 2 in the front view has been obtained. So this is point number 1, 2. Next, point 2 we are going to locate. So from point 2, vertical projector we have drawn. Please check, we have not numbered it yet. This is point 1, this will be point 2. Why this is point 2? This is the vertical projector drawn through the point 2. This is horizontal projector drawn through the point 2. So wherever these two intersect, this gives me the location of point 2, 2 dash in the front view. Then this is point 3. So from point 3, I have drawn a vertical projector upwards. Wherever it intersects with the horizontal projector drawn through the point 3, 1 dash over here, this gives me the location of the point 3, 2 dash in the front view. So I am not labeling it yet because it would have created too much of points over here. So this is point 1 in the front view, point 2 in the front view, this is point 3, because a sequence we are going to follow, so it's easy to remember. Point 1, point 2, point 3 in the front view. Let us move to point 4. So from point 4 2, we have drawn a vertical projector upwards, and from point 4 1 dash, a horizontal projector we have drawn. Wherever these two intersect, point 4 2 dash will be obtained. Similarly, from point 5 2, we have drawn a vertical projector upwards. Wherever it intersects with horizontal projector drawn through phi 1 dash. This gives me the location of point phi 2 dash in the elevation. So 1, 2, 3, 4, 5 points in the elevation they have been obtained. Now from point 62, please check. This is point 62. We have drawn a vertical projector upwards, and wherever it intersects with the horizontal projector drawn through the point 61 dash, this is 61 dash. So wherever it intersects with projector drawn through 61 dash, so this is the intersection. So this gives me the location of point 62 dash in the elevation. Now this is the point 7 over here. From point 7 we have drawn a vertical projector upwards. Wherever it intersects with horizontal projector drawn through point 71 dash, this gives me the location of point 72 dash. Then this is point 8. We have drawn projector upwards. Wherever it intersects with horizontal projector drawn through point 81 dash, this is the location of point 82 dash. Then point 92 over here. Take a vertical projector upwards. This is horizontal projector through 91 dash. So vertical and horizontal projectors corresponding to point 9 wherever they intersect. This provides us with the location of the point 92 dash in the elevation. Then this is point 10.2. From point 10.2 we have drawn a vertical projector upwards. This is location of point 10.1 dash. So wherever it intersects with the horizontal projector drawn through the point 10.1 dash, so we obtain the point 10.2 dash over here. And this is point 11.2. So we have drawn a vertical projector upwards from the point 11.2, and this is the point 11.1 dash. So from 11.1 dash we have drawn a horizontal projector. Wherever these two projectors they intersect, this provides us with the location of point 11.2 dash. And finally this is point 12.2. Now from 12.2 we have drawn a vertical projector upwards. This is point 12.1 dash. So we have drawn a horizontal projector from 12.1 dash. Wherever it intersects with the vertical projector from 12.2, we obtain the point 12.2 dash over here. So point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All the 12 points they have been obtained in the front view. Now you can see the numbering has also been made. 1.2 dash, 2.2 dash, 3.2 dash, 4.2 dash, 5.2 dash, 6.2 dash, 7.2 dash, 8.2 dash, 9.2 dash, 10.2 dash, 11.2 dash and 12.2 dash. And once we join, we can see that this is the final apparent shape of the circular lamina, which is oblique in nature. That is, it is inclined with respect to HP at an angle theta, and the plan of the diameter, it is inclined with respect to the vertical plane at an angle of 30 degree. So this way the oblique front view projections they have been obtained. This way oblique apparent shape projections in the top view they have also been obtained. Now this is all for today. So I hope that through this discussion you would have understood about the procedure to evaluate the apparent shape projections of an oblique circular lamina which happens to be inclined with respect to the horizontal plane as well as with respect to the vertical plane, right? So we are going to continue with further discussion regarding few more illustrative cases of orthographic projections of the planes in the coming lectures. So thank you very much. Thanks a lot.